Hello students, in this video we'll discuss the geometry of vector addition and scalar multiplication. So let's suppose that we have two vectors v and w. We can write down representations of these vectors, so consider the arrow, which starts at the origin, and goes to x, y, z as the representative, canonical representative of v. So since v is a collection of arrows that are equivalent to each other, I can pick the arrow that starts at the origin and goes to some fixed point. That's the canonical representation of v. And so what we'll do is we'll write, so in three-dimensional space, we'll start at the origin for v and go to a point x, y, z. So this will be one of my representations of v. And then what I'll do for w is, for w, pick an arrow which starts at x, y, z and goes to another point we'll call this point x tilde, y tilde, z tilde, where w has this representation, is the collection equivalent to the arrow x, y, z to x tilde, y tilde, z tilde. And so we'll do that. That will be the point x tilde, y tilde, z tilde. Then the arrow from 0, 0, 0 to x tilde, y tilde, z tilde is a representative of the sum vector v plus w. So we oftentimes refer to the vector addition problem as saying that if you want to add the vector v to the vector w, what you do is you put the tail of v, the tail of w, at the tip of v. So this point over here is the tip of v, and this point over here is also the tail of w. So you tip to tail for the vector v to the vector w, and then I connect this, and that vector over here will be the vector v plus w. And so we see from this that we actually get more geometry that pops out of this vector addition. What we see, for example, is if this is my vector v, let's say this is my vector v over here, and this is my vector w. Then what I can do is I can write down an equivalent representation of w. If this is w, then this vector in the same magnitude and same direction, this arrow over here, is an equivalent way of representing w. So w can also be put over here in this representation. Analogously, we can put another representation of v up here, and they have the same magnitude and same direction. So this is parallel to this, and this is parallel to this. In other words, using these two vectors v and w, I can construct a parallelogram. And then this vector over here will be the vector v plus w. So v plus w is one of the diagonals of the parallelogram. And we can do a similar idea and look at the vector v over here. And now the vector negative w goes down like this. So that's negative w. And I can slide, so we see over here W is in the positive orientation, over here W is in the negative orientation. I can do another copy of V over here. Another copy of negative W over here. And now I can look at this diagonal over here. This diagonal represents this vector V plus this vector negative W, so this other diagonal is V minus W. So if I look at over here in this configuration, if I draw this vector over here, this vector over here is V minus W. And what we're able to do is we're able now to represent vector addition and vector subtraction as the diagonals of a parallelogram whose sides correspond to the sides of length V and W and the corresponding directions associated to the direction cosines. Thank you very much.